Okay, welcome to your fourth video. I'm going to be finishing up 1.3 today and then also beginning 1.4, probably finishing it. Okay, so a couple of things for you to pay attention to on this video. Today, I would say, is more AP-ish than anything we've done so far. Like, what I'm going to do today can literally be on your exam in May as an FRQ. Okay, so try to hang tight with that. It's also, I can assure you, going to be very closely aligned to our first test. So I've already talked to you about how you could have a powder that's like carrying around water with it. It would be a hydrated powder. And we're going to do a lab where we talk more about like our Unit 1 lab. When we heat a substance, like if there's water associated with that, or if like when that substance is heated, it releases gases like CO2, then you're going to lose mass as you heat that compound because those gases are going to evaporate, like water gas or water vapor or CO2 gas, anything like that. And when you end up with the compound that no longer has water with it, that's called an anhydrate. A in front of a word usually means not. Okay, so an anhydrate is a compound that is dried or contains no water any longer. Now, we will say that we drove off the water. That actually is a way that we will like discuss this, driving off the water by heating it. So you'll always be given data, and you'll be given like a container, which is often called a crucible. We'll be using a crucible in our lab when you come here in August. But I did use one last year with, so if you're a junior, we did that blue powder in a crucible. It's like a little porcelain bowl. But if you look here, they're telling you, hey, we had a hydrated compound. It was magnesium chloride, that raised dot, and we don't know how many molecules of water this compound had. We heated it, and when you get the mass to stop going down, like we say, it's reached a constant mass or it quits decreasing, then you know that you're done heating it and you have driven off all of the water. So when it says, how can the student say the hydrate was heated a sufficient number of times, you're going to say it reached a constant mass. Now you're going to fluff it up a little bit if it was a real FRQ. You don't have to say complete sentences if it was a real FRQ. Bullet points is sufficient. It's not like AP Bio where you got to write paragraphs. I'm not saying you have to write paragraphs, but I think AP Bio likes complete sentences. I could be wrong about that. But you're going to want to say the substance reached constant mass, or it stopped losing mass when being heated. So then you would want to say, like, we do a lot of therefore statements in AP Chem. So you would say something like, therefore, all of the water of hydration, that's what we call those water molecules, was driven off because you no longer had mass going down as you heated the compound. In fact, it went up a little bit. So you want to stop for sure. Now, it says, hey, give me the total number of moles of the water lost. The mass lost was the water. Okay, that's what you did. You heated it to lose the water, the mass. So you're going to say, okay, 25.825 grams minus 23.976 grams is the mass of the water that was lost. I'm just getting it from up here, the sample and the container, okay, minus what happened when you got it to where it stopped losing mass. You could subtract the mass of the container, but you don't really have to, okay, as long as the container's in both of your numbers. Now, it says moles. I'm in grams, so I got a molar mass for water, 18.02 grams in 1 mole, 0.1026 moles of water. If they want the formula of a heated, hydrated compound, it is like doing empirical formula. You get the number of moles of the substance, and then you divide by the smallest number of moles. It's exactly what we do with empirical formula, okay? So what I do here is I say, okay, let me see how many moles I had of magnesium chloride. I already got my number of moles of water. because you got to divide by the smallest number of moles to get their ratio together. So if I say, all right, 23.977 minus 22.347, that is what would tell me the number of grams I have of magnesium chloride. I'm just getting that from the chart, okay? And if I flip that to moles using molar mass, that means I had 0.01712 moles of magnesium chloride. So now I've got moles of the water and moles of the other thing, like an empirical formula, where then I have to divide by the smallest number of moles. Well, this is the smallest, okay? 0.01712 divided by 0.01712, and then for the water, 0.1026 divided by 0.01712. This is 1 and this is 6. Remember, this was the magnesium chloride and this was the water. Okay, I'm getting these numbers from over here highlighted in blue. So that just means that there was 1 mole of magnesium chloride, and there must have been 6 moles of water. So that's 6. That's how you get the formula for that. Now, it's like empirical formula. Every time you see these, you always divide by the smallest number of moles, and the answer you get, you're used to thinking of the answer you're getting as like your empirical formula subscripts. You're not doing subscripts here. You're doing it as like formula units or moles of water. Okay, so it's very similar to empirical formula, and I want to take a look at that, but it's also a little bit different. Something else that you're going to be asked to do is to do combustion analysis to figure out the formula of a hydrocarbon. A hydrocarbon is a CH molecule. Okay, we talked about this in honors. All right, a hydrocarbon is some kind of CH, and the definition of combustion is that you burned it in oxygen. You were required in honors to memorize that the products of combustion are CO2 and water. Remember, we hate balancing these. They're hard. Everybody's mad about it because it's usually an odd number in front of the oxygen, like a 7 or a 9, and it just makes everything hard. That X and that Y after the C and the H is just basically telling you I don't know the subscripts for that. To do a combustion analysis, you're going to have to be given the amount of the products that you get. Once you know how much CO2 and water you have, you can then do mole ratios to determine how much carbon you had and how much hydrogen you had. Because all of your carbon came from that guy and all of your hydrogen came from that guy. So if you can see how many moles you had of C and how many moles you had of H, then you can figure out your X and Y, or your formula of your hydrocarbon. Well, how do you do this? And I apologize, when I did this last night, I was like, oh, I didn't leave them a lot of space for this. All right, well, first you do like you always do, write down what you know. What do you start with? The product of CO2 and water. And as it is usually in chemistry, when you have grams, you have to go to moles. And I will tell you the main reason I'm going to moles is because I'm trying to do a mole to mole comparison. Okay, so I'm going to do molar mass, CO2, and water. Okay, so now I've converted to moles of CO2 and water. But I don't really care about CO2. I care about C and I care about H. Why? Because I'm trying to figure out this right here. I'm solving for this formula. Okay, I'm trying to get to C and H. So now I'm going to say, ooh, I can do this. If I have 1 mole of CO2, there's 1 mole of C in that. Remember, there's like an imaginary 1 right there. And they're like in a 1-to-1 ratio with each other. And if I have 1 mole of H2O, there are 2 moles of H. Remember? Because of that 2 right there. Now I'm doing good. I've gotten now to the C and the H, which is the meat of the problem and what I'm actually trying to solve for. Okay. So if I do the math here, you're going to see that this term, that's a highlighter, that this turns out to be 1. And when you do 45 divided by 18.02 times 2 over 1, this turns out to be 5. And that is your subscripts. It's very similar to empirical formula. We're not calling it empirical formula though. Well, I mean, you are calling it empirical formula. I just don't think they're always going to say the word empirical formula. Maybe they will. But if you're given a combustion analysis and you're given information about the CO2 and the H2O, you're trying to take your grams of the compounds, get to the elements themselves, and then let that be, those numbers be your ratio or your subscripts that would go after your C and your H. I guess what I was thinking a minute ago is when they ask for the formula of the hydrated compound, they're not going to call it empirical formula. But it's all very similar to just solving for an empirical formula. So you're going to do this one by yourself, 1.3F, and right here, and then you're going to have answers. See all the answers right there? Okay, so do those. Let's take a look really quick at mixtures. We did a flowchart in honors very similar to this. You can have a homogeneous mixture or a heterogeneous mixture, meaning like a chocolate chip cookie would be heterogeneous, or a homogeneous would be like the mixture of air that we breathe, like of nitrogen and oxygen and all that, the gases that we breathe. Remember, elements and compounds are not pure substances. Elements and compounds are pure substances. They're not mixtures, but you can combine 2 or more pure substances to form a mixture. Now, this section is all about trying to do what's called elemental analysis or mass percentage. So you can determine the mass composition of substances in a mixture. Well, of course you can. You just saw where we had masses given to us when we were doing empirical formula. We will be doing stoichiometry or mole ratios to solve these problems. The mass percent of something in a substance is basically the mass of the individual substance divided by the total mass of the mixture, okay, times 100. Now that's easy. It's the same thing I said a minute ago. Like if you have 100 grams of substance and you have 70 grams of that is sulfur, then you have 70% sulfur, okay? Now, elemental analysis, which is sort of what you just did a minute ago when you were doing that combustion analysis, because you were trying to see like of the elements C and H, okay? But elemental analysis is used to determine the composition of a mixture. Maybe it's just to qualitatively tell me what elements are in it, or quantitatively tell me the amounts of the elements that are in it. This is called analytical chemistry. No one's going to ever ask you that. Combustion analysis that I just showed you is one way to do that. Okay. So we would know, like, and showed you a minute ago, that all of the carbon would go into carbon dioxide, all of the hydrogen would have gone into water. Now, if I had nitrogen in a combustion problem, then that would all go into nitrogen monoxide or dioxide. In other words, I would take the balanced chemical equation to compare mole ratios, okay? This one is a little bit different. I'll be honest with you, some of these are a little bit common sense-ish, okay? So you may actually have a different method than I'm about to show you, but let's look at this one. 2.4 grams of a mixture that contains this and this, okay? But they want to know of both of those things together, what percent of that 2.4 grams is only the NaCl, okay? Well, we got to have something that we can work with. They said to you, hey, the NaCl, we know that it has that much sodium in it. So you're going to have to take that amount of sodium to see how much NaCl you had, okay? Well, we know that, like, we can compare the amount of sodium versus the whole compound sodium chloride. Okay, we've already kind of done that today. Let's start. 0.12 grams of Na. Well, we know that if we're going to do stoichiometry or mole-to-mole ratios, I've got to be in moles. So I'm going to molar mass that, 22.99 grams, or in 1 mole, periodic table, and you're going to get 0.00522 moles of sodium. Now, you can start doing scientific notation if you want. 5.22 times 10 to the negative third. Okay. If you want to go to tech, you probably should start doing scientific notation. You should get used to it. I don't do it often though. In AP would accept either way. Now, so if I know that's how much sodium I have, well, how much sodium chloride did I have? Remember that idea of me telling you that it would be a 1-to-1 ratio? Like if you have 2 moles of NaCl, there's 2 moles of Na in that. If you have 2 moles of NaCl, then there are 2 moles of Cl. They're in a 1-to-1 ratio with each other, with the whole compound, because there's a subscript of 1. That is the most abstract part of stoichiometry. What am I saying? I'm saying that if I know that that is how much Na I have, that's also the number of moles of NaCl I have, because they're in a 1-to-1 ratio together. Okay, put a star by that if you're struggling with that. Now, because I know that to be true, I now can see how much I had in grams of NaCl. Now I'm just going to go backwards to get to grams using molar mass. 1 mole of NaCl is 58.44 grams. That means I have 0.305 grams of NaCl. So by studying the Na, I could get to the NaCl. By getting the NaCl in moles, I could get to the grams. Now I can do mass percent, which basically says 0.305 grams of NaCl in the total 2.4 gram sample times 100 equals 12.71%. So of that total 2.4 grams, 12% of it was NaCl. The other was the calcium chloride. Look at this question. What I would like for you to do is pause the video and try to answer this by yourself and then come back. The mass percent of glucose is supposed to be 40%, but there's an impure sample, and we know that it's too low. The carbon that was supposed to be 40% is 38.2%. So we're like, there's a low mass percent of carbon, so something has contaminated this sample. This actually was an old exam multiple choice question. They didn't ask you to explain yourself. They just asked you to choose, but I'm going to ask you to explain yourself. Okay, so the correct answer is A. Okay, and let's talk about it. Ribose, this should be fructose. Ribose and fructose actually have the same empirical formula as our guy up here at the top. So they're not going to have a different percent. They're not going to affect that. Okay. Water, though, would cause the percent of carbon to decrease because you added H and O. Think about that. If you add H and O, think about how your fraction would be. Okay. If you are going to add to the total mass, but you didn't add carbon, you've decreased your percent by mass for carbon. And down here, this is adding everything. It's adding like C12H22O11, but it is definitely going to end with the percent carbon being increased. Okay, because you're adding carbon. I was trying to think if you guys were going to be thinking though about how the it is still the same empirical formula. Oh, no, it's not. It's not the same percent. It's not the same. I was just checking that and it's not. So it's not the same empirical formula like ribose and fructose. I don't have the formula for sucrose memorized. I'm trying to make sure that's not a typo. I don't think it is. Okay, I'll come back and address that if it is. All right, the answer is water. It's going to be the contaminant because you definitely need to get used to this year manipulation of fractions. I don't talk a whole lot about it in 10th grade, but think about anything. Like we're going to talk about something later that looks like this. Okay, I don't know what that is yet, but just looking at this as a fraction, if you increase the numerator, then you increase this answer. Okay, those are directly proportional. If you are going to like, what if you looked at the manipulation of this fraction and you like decrease the r squared? That increases the f. They are inversely proportional. Okay, so just kind of like try to think about how fractions can be manipulated. We're going to do a lot of things this year, which are like, sometimes you can plug in fake numbers to try to manipulate the numbers, but you also kind of got to have some conceptual thoughts for numbers. Okay, I want you to do 1.4c by yourself. I'm going to give you the answer. The answer should be 75%. Okay, you're going to do that one by yourself. And when we look at precipitation, or like what you did last year when you made a precipitate, okay? Remember we did our chalk lab? I don't think you do that with Miss Ladard, but when you do precipitation gravimetry, that is basically making a solid from a double replacement reaction. Okay, remember we talked about this last year. We said, okay, if you have an aqueous thing plus an aqueous thing, two compounds, you would yield another compound that would also be aqueous, and then there would be another compound that would be insoluble, and it would be a solid, S. And we said snaps never make a solid precipitate. Those are always soluble in water. They are sodium, nitrate, ammonium, and potassium. Okay. And we're going to try to remind ourselves what those are. So sodium is an ion that never makes a snap. Nitrate, you were supposed to memorize. It never makes a snap. Ammonium, it never makes a snap. And that was a weird one for you to memorize. Potassium, it never, not never makes a snap. Sorry, it never makes a precipitate. You can tell I'm trying to rush. So these four ions are never going to be the thing that makes the precipitate. I will tell you, the most common precipitates are barium sulfate, lead sulfate. You can see that here, lead sulfate, and AgCl. They're the most common precipitates. So in this type of chemistry, when we do this, the analyte, or what we are analyzing or studying, is converted to a precipitate or a solid that is insoluble. Well, why? Why in the world would we want to put these two aqueous things together to get this solid? Because once we can filter it, clean it of any impurities, and weigh it, it will allow us, it's almost like getting that CO2 and that water from that combustion. It will allow us to have information about a product that will tell us other stuff about our reactants. It's still that mole-to-mole comparison. So it'll help us determine the amount of a substance or the mass present. So it's still being used to help us get like the composition of a mixture. Okay, here's a good example. A student's given a mixture of NaCl and sodium nitrate. Some bells should be ringing in your head. You should be like, ooh, snap. Ooh, snap. Ooh, snap. So you're like, okay, they're not going to make a precipitate. So there must be something else that's going to come along with that chloride and make a precipitate. So what happens is they're solids, they're ionic solids, and I'm going to put them in water. It says, hey, I'm going to dissolve them in 50 mLs of deionized water. That's what DI stands for. And then after I do that, now that I've got a mixture of sodium chloride and nitrate, I'm going to add silver nitrate. Okay. Remember, he's a snap. Silver's not. And didn't I just tell you that AgCl is probably the most common asked about precipitate? So I'm reading this and immediately I'm like, ooh, I bet AgCl is going to fall out as a solid. And they're like, hey, here's the reaction. And there it is. Okay. They're saying, I'm going to combine sodium chloride. I'm going to add this excess. Often whoever is being added to like cause the precipitation reaction, it'll say there's excess of him. And so I remember it's the same idea of I have now information about a product to help me get information about the reactants. Okay. It's just like that combustion analysis. So it's like what we're trying to get you to tell us is something about this reactant, but you're going to have to start with what you know. Well, what do you know? You don't know anything about NaCl, but you do know about this guy. You had 2.268 grams of AgCl. Well, I can't compare AgCl to NaCl unless I do mole-to-mole comparisons. Remember, that is stoichiometry. It's basically remembering that you can use these molar coefficients in front of these compounds as mole-to-mole ratios. So remember, I can't do mole-to-mole if I'm in grams. I'm going to go grams to moles using periodic table for AgCl. Now, remember, I'm trying to compare AgCl to NaCl, mole to mole. Why? Because I'm trying to study NaCl. And I know that the problem is asking me about grams or mass. The problem is not asking me about moles. So I'm going to say, okay, now I've got to take the moles of NaCl and flip that back to grams of NaCl, 58.44 molar mass. Add up the Na and the Cl from the periodic table. And that leads me to come up with this. Now, how am I doing all these? I know I'm not like explaining the calculator work. You can treat these as one big, long multiply across the numerator, divide by the product of the denominator. You can put it in your calculator like this, 2.268 divided by 143.32 multiplied by 58.44. What I do suggest, and I did teach you in 10th grade, is not to do a whole bunch of parentheses and fraction bars in your calculator. Like my calculator would look like this, 2.268 divided by 143.32. I would go ahead and hit enter and get an answer. Then I'm kind of neglecting this. It's 1/1. So I don't really have to do anything with that. Okay. Then I'm going to hit auto populate answer and multiply that by 58.44. I'm not going 58.44 over 1 in my calculator. Why would I do that? That 1 is like nothing. It's like any number over 1 is just itself. Okay. I do not suggest doing that. The more keystrokes you put in your calculator, the more likely you are to hit the wrong button. Now that tells me the grams of NaCl, but I want to know the percent. So I'm going to say that over the total 3.613 grams of the mixture times 100 equals 25.6%. Now, they gave you the balanced chemical equation up here, but there's going to be times when you have to come up with that equation. We're going to practice that throughout the year, okay? But that is a very, very good question and something that you could expect to see in May, okay? So I really like that one. And that's when we did our chalk lab last year, trying to get you ready for this kind of stuff. So now I want you to do the additional practice questions right here. You're going to get your answers right here. And then lucky for you, the next section goes into electron configuration, like 1s2, 2s2. And the reason I say lucky for you is you're leaving moles for a little bit. And you are now halfway through Unit 1. Okay, so you're almost halfway through Unit 1. Well, you are halfway through Unit 1, so you're almost ready to tie a bow on this. So hang tight, be strong, and email me if you have any questions.